Hey everyone, welcome back to Everything Mathematics. Did you ever understand the concept of even and odd functions? Do you know how to tell when a function is even or odd algebraically or graphically? Today, my goal is to show you exactly how to do that. By the end of this lesson, you should have a pretty good understanding of this concept and you should be able to apply it to other areas of mathematics. Let's take a look. Here we have four graphs of functions. They all seem very different, but they have a particular unique feature in common. I want you to take a look. Notice how all of these four graphs are symmetric about the y-axis, completely symmetric. For example, I'm going to take the very first parabola as an example here. Notice how this portion on the right of the y-axis is identical to this portion on the left of the y-axis. And if you notice, the same thing happens here with this one. The right and the left are identical. Same scenario with the last two graphs. That means that these functions are symmetric about the y-axis. Moving on to this one, we see exactly the same feature as the previous four functions. Again, symmetry about the y-axis. Well, this is what it takes for a function to be even. A function is even if it's symmetric about the y-axis. Imagine that this square over here was a tiny piece of paper. If you were to actually take that paper, let's pretend, and you fold that paper along the y-axis, you create a crease along the y-axis, then this part of the graph will match perfectly with this part of the graph on the other side of the y-axis. So then we are going to put that into writing. We are going to say that a function is even. So a function is even if it is symmetric about the y-axis. Okay. Now, analytically or algebraically, let's say, you can also determine when a function is even. I want you to notice this over here. Let's say that I take -2, and then here I take +2. I want you to notice something here. If I go all the way up to my graph at -2 and 2, notice how the y values are identical, right? Which is, it goes back to the idea of being symmetric about the y-axis. Then that is telling me that f of -2 is equal to f of 2. And this is consistent for every single x in the domain of this function. So now I can make the following generalization. I can say that f of -x is equal to f of x. And this is what makes a function even. If this particular property here is always satisfied, if you can always show that f of -x is equal to f of x, then the function is an even function. It is perfectly symmetric about the y-axis. I want to show you now how to show that a function is even, a function like this one or this one right here, without a graph. So let's take a look at this one. Show that the following functions are even. Well, this is a rational function. I don't have a graph, yet they are asking me to show that this graph is even. And what I plan to do here is to use this analytic relationship here. I'm going to show that if I start with f of -x, and then I do a little bit of algebra, I should end with f of x. So this is what I have in mind. F of -x. I'm going to go ahead and I'm going to take my function, and wherever I see an x, I will substitute negative x. This is what this notation means. So we're going to have now negative x squared divided by 4 negative x to the fourth minus 2 negative x squared plus 1. Notice again that I substituted negative x in place of x. Then now simplifying, this will be equal to x squared divided by 4 x to the fourth minus 2 x squared plus 1. I want you to notice how the negatives disappeared because I was raising negative x to an even exponent in all 3 cases. So then that means that if you raise a negative number to an even exponent, the negative disappears. The result becomes positive. So everything became the same. In fact, this is exactly equal to the original function. And this is now what shows that we end up getting f of x. So our conclusion is that since f of negative x ended up equal to f of x, then f is even. Okay, so we showed exactly the analytic relationship that f of negative x is equal to f of x. Then that means that the function is an even function. It is that easy. Now we're going to go ahead and we're going to look at g of x equals cosine of x. We're going to follow a slightly different approach in this case, a less algebraic approach. So notice here how we have the graph of cosine. So beautifully symmetric about the y-axis. This part over here is identical to this part over here. So then it is clear to us that indeed f of negative x is equal to f of x just by looking at the graph. Now, another way that we can convince ourselves that cosine is an even function is by analyzing cosine within the unit circle. So in that particular case, this is what we're going to do. Imagine that I consider theta. In fact, I'm going to switch to theta here. Instead of using x, I'm going to think of the function g of theta equals cosine theta. Since we're going to be using the unit circle, it's going to be easier for the brain if we do that. So imagine that I consider this angle theta right here and this one negative theta. Then if you notice, I now have the terminal side of theta nicely intersecting at a point on the circle, and then the same thing over here. So I'm going to put a point over here and a point. Now this point has coordinates x comma y, and the same thing with this one, x comma y. You may remember from your early studies of trigonometry, particularly of the unit circle, that we can also re-express the coordinates of these points right here using the trig functions. So this becomes cosine theta and this sine theta for the y value. And then in this particular case, we're going to have cosine of negative theta and then sine of negative theta, just like this. And just a quick refresh as to how these expressions come about really quickly. You may remember, again, from the start of trig, that, for example, by definition, cosine theta is equal to the adjacent side over the hypotenuse if you're thinking about triangles, or if you're thinking about just simply ratios, it is equal to the ratio x over r. Now, in this case, remember that I am using the unit circle. Unit means a circle with radius 1. So then that means that this r over here is going to be equal to 1, which means that cosine theta simplifies to just x. Then if we do the same thing with sine theta, if you remember, by definition, is equal to y over r. And because we're working with the unit circle, r is 1. So then you end up getting that y is equal to sine theta. So just a quick refresher as to how these coordinates come about. So then now let's go ahead and continue with the analysis. Notice over here, I'm going to go down to the horizontal axis and then to the other point. Notice precisely how the x values of these 2 points right here, they are exactly identical. They fall exactly at the same location, which really says that cosine theta, what this is saying is that cosine theta is equal to cosine of negative theta. So this cosine theta right here is identical to cosine of negative theta. So cosine is an even function. Now, let's turn on to odd functions. Here I have the graphs of 3 different functions, and they all appear to have a different shape. Now, in this case, if you look very closely, you do not see symmetry about the y-axis. They are not symmetric about the y-axis. But there is another feature that they all have in common. It's a little bit different. Something that maybe you may not be able to see, to detect right away, but there is something particular about them. There's something unique about them. It is symmetry, but it's a different type of symmetry. I will explain this right now. So here I have this graph, which is just like the previous ones. Again, not symmetric about the y-axis, but there is symmetry. Look, if I take the right part of this graph right here, and if I reflect it about the y-axis, I'm going to go ahead and do that. And this will not be perfect. That's okay. I'm going to go ahead, imagine that we do this. We reflect about the y-axis. If we do that, I get this graph, this piece right here. So what I did was, again, just to recap, I took the right part of the graph, and then I did a reflection about the y-axis. Notice how now the green and the red, they look like a W. And if you now take the red and you reflect about the x-axis, you're going to get exactly this piece over here. So now then, what I did was a double reflection. I took the right side of the graph, this part over here, I reflected that about the y, and then I take the red, and then I reflect it about the x-axis. And that's how this red part matches perfectly with this one over here. And then you get the full graph exactly as it was given to you. A double reflection gives you the same outcome. This is exactly what is peculiar about odd functions, that if you do a double reflection, one reflection about one axis, let's say the y-axis, and then a reflection about the x-axis, then the graph remains the same, nothing changes. Now, a mathematician may think of an odd function in a slightly different way. A mathematician may think of an odd function as a reflection about the origin. Let me show you exactly what I have in mind. Let's say that I take this particular point on my graph. If you notice, this is the origin. I take that point now and I reflect that point through the origin or about the origin. So in other words, the line of reflection is the red line that I just drew here. And notice how that line of reflection passes beautifully through the origin. So if that's the case now, notice how the point that we started with, let me use a different color. I'm going to use blue here. So we started with this point right here. Notice how this point travels along this line that passes through the origin and lands here on the other side of the graph, but in a symmetric fashion. So right here, I'm drawing that point there in blue. So Mathematicians tend to think about odd function in this particular way, as performing a reflection of a point on one side of the graph through the origin, and then it lands on the other side of the graph. And functions that behave like this, functions that have this type of symmetry, are said to be odd functions. Let's do that again with another point. I'm going to pick this point right here. Let's say right here. If you notice, right here in the fourth quadrant. And I'm going to go ahead and do the same thing. I'm going to do a reflection by taking that point through the origin, and then notice how it lands right over here, right here. So perfectly again, we take the point is reflected about the origin by passing through the line that goes through the origin, and see now how it beautifully, in a symmetric way, it lands on the other side of the graph. So odd functions must behave like this all the time. All right, so now I'm going to say over here that a function is odd if it is symmetric about the origin. This is the more descriptive definition. Now you can also think about it, as I said earlier, that an odd function is symmetric by performing a double reflection. One reflection about one axis and then a reflection about the other axis. That's okay too. Now analytically, how do we show that a function is odd? So I'm going to go ahead and I am going to pick this point right here. So we're going to pick this point right here in quadrant number 3. And then we're going to also work with this point over here on the other side in quadrant 1. So I'm going to go to the x-axis, and roughly I'm going to say that this point has an x value of negative 1.5, and therefore because of the symmetry of the graph, this is going to have an x value of 1.5. And I want you to notice now that when I look at the corresponding y value right here, this will be f of negative 1.5, whereas this one over here is going to be f of 1.5. Now, there is a striking difference, right? F of negative 1.5 as a y value is going to be negative. It is below the x-axis. This one over here, f of 1.5, this y value is above the x-axis. So this will be positive, positive, negative. So then this is saying that f of negative 1.5, remember that this is a negative number, will be equal to minus f of 1.5. So here is very important. I need you to remember that f of 1.5 is a positive number. F of negative 1.5 is negative. So the only way that I can have equality is if I place a negative right in front of a positive number. So now a negative number on the left equals to a negative number on the right. Now I have equality. And now I can generalize this statement by using only variables. So a function is odd if and only if f of negative x is equal to minus f of x. Okay, so this is what makes a function odd. And now I can use this relationship to algebraically show that a function is odd. So here I have this particular function f of x is a cubic polynomial, and they're asking me to show that this function is odd. And then later we're going to do sine. So how do we do that? in a very similar way as with the even function that we did a while ago. We're going to start with the left side, f of negative x. We're going to substitute negative x into the variables here, and then we're going to simplify, and we hope to get negative f of x. So let's try that. So we're starting with f of negative x. We now substitute negative x in place of x, right? I'm hoping that you can see right there how we substituted negative x in place of x. Then minus 2, substituting again negative x, and now simplifying. When we simplify, take a look at this expression. We are cubing a negative number. Cubing means odd exponent. If the exponent is odd, then a negative number raised to an odd exponent will be negative. So then we're going to end up getting a negative outcome here times a negative that was already in the front. That will become positive x to the third. Similarly here, a negative times a negative, that is going to beautifully give us plus 2x. And now notice how this expression right here, looks similar but still not the same as this one. Well, what happens if I now factor a negative out? I know that you don't see it there, but just pretend that you factor a negative out. If I factor a negative out, now I'm going to have to adjust the signs of the terms that are going to be in the inside of this set of parentheses. So we're going to have negative x to the third minus 2x. Look at this. If I were to distribute again, I would have a negative times a negative, positive. A negative times a negative, positive. But now I want you to notice that this expression inside of my parentheses here is precisely f of x. Is exactly this expression right here. So then what I have now is that this is equal to minus f of x. And this minus outside was the one that we factored out right here. So now in conclusion, we showed that f of negative x is equal to f of x, which really means that f is odd. And this is pretty much the type of algebra that you always do whenever you want to show that a function is an odd function algebraically. Now in this case, the last one, g of x equals sine x. Here you can see immediately again, this is the graph of sine. That sine exhibits the symmetry that we were talking about the origin. Look, if I take this point right here and I reflect it nicely about the origin, this is what we will get. So I take this point and I take it all the way through the origin. We get precisely the point landing right here on the other side. So we took it on the first quadrant, we reflected that point about the origin, and it beautifully landed here on the graph itself, but on the other side, on the third quadrant. So this really says again that we have symmetry about the origin. So graphically, we are seeing that sine is an odd function. Now we can also do the same thing with the unit circle. We are going to switch from variable x to theta for the sake of simplicity with working on the unit circle. So we're going to consider g of theta equals sine theta. And now over here, we're going to have a positive theta, and here we're going to have a negative theta. So then, again, as always, look at the terminal side of theta and the terminal side of negative theta. we're going to have an intersection right here on the circle, and that's going to give us a point with coordinates x comma y, and the same thing over here in the fourth quadrant, x comma y. You may remember that we can rewrite the coordinates in terms of trig. That means cosine theta, sine theta, and here we're going to have cosine negative theta and sine negative theta. And now what we are going to be doing is we're going to be comparing the y values of these points, sine theta versus sine negative theta. What I want you to notice is that now, because we're talking about the y values, we're going to go ahead, we're going to go across to find the y-axis, and in this case, this is going to be sine theta right here. And you notice how sine theta is now above the horizontal axis. And then in this particular case right here, same thing. This will be sine of negative theta. So then you notice that just like in the graph here on the left, you have that sine theta is above the horizontal axis, so it is positive, and here sine theta is below the horizontal axis, so it is negative. And if we are going to set them equal to each other, we're going to have to make a minor adjustment. We are going to say that sine of negative theta is going to be equal to minus sine theta. We cannot just say that sine of negative theta equals to sine theta. That will be wrong because a positive number cannot equal to a negative number. But then, if you remember, sine theta is positive. So then by putting a negative in front of a positive number, we're going to get a negative. And now we have nicely that a negative number is equal to another negative number. When you consider both of these over here, you're going to get one big negative number. So all these together is negative. So now nicely, a negative number equals to a negative number. So this is saying that sine theta is odd.